Hello everybody. So what you see here is a problem that I included on our assignment regarding a mass attached to a spring with something that dampens the vibration as the mass is displaced from rest. Okay? Because there's a dampening force on the mass, then the oscillation or movement is going to look something like this. It will be a cosine wave back and forth like harmonic motion, but this coefficient that's exponential is going to dampen it, decrease the amplitude over time. Okay, now we don't have to analyze that part of it, but that is what's happening. If I can look at the vertical axis, which tracks the up and down motion of the mass as it's displaced and let go, then it would look a lot like that. All right, but here's our objective. If that's the function that describes the up and down motion of this object, what is the average value of that function? And I look at it like, well, why? Sometimes it's positive, sometimes it's negative. It's going to take a range of different values over the course of time, and I want the average value. So, okay, here's how we do that. First, let's talk about what is the average value of a function at all, because that's what we're being asked to find here. The way that works is this. So to find the average value of a function, then you have a function on some closed interval. Okay, so I might say, well, there's this function f of x on this interval from a to b. So like x runs from a to b inclusively. If that's the case, the average value of the function on that closed interval is 1 over b minus a times the definite integral from a to b f of x dx. Okay, so that's what we need to do. In this case, as that problem was described, my function which tracks the up and down oscillations of this mass is 6 times e to the negative t power cosine t, and the clock was running from 0 to pi. All right, that's the interval, 0 to pi right there. The clock's running, the mass is oscillating. So I've got, as I should, to find the average value, a function and a closed interval. So if I apply this general definition to this scenario, then here's the integral that I need to calculate. All right. So what I will do to work this is I notice that our function, which tracks the movement of this object, has a coefficient of 6. That's a constant. I can factor out constants out of integrals, and I'll go ahead and do that. So I get a coefficient here of 6 over pi. Now, the way I would work this integral with the fundamental theorem of calculus is to find the antiderivative of e to the negative t times cosine t. So long as I can find that, I can evaluate this integral. Okay, and there are lots of ways to find antiderivatives. Maybe there's a basic, simple, general formula that you use. Maybe there's a technique like u substitution or integration by parts, something like that. So how we find antiderivatives would depend on what we have. In this case, the way that we'll calculate this antiderivative is with integration by parts. All right. In general, that is the way that we can find the antiderivative of an exponential times trig function, sine or cosine. Okay. Now, for this particular kind of problem, I've already made a video about how you would solve it. Okay. So what I'll do is I'll tell you, well, part 1, I want to find the antiderivative of e to the minus t cosine t. But I'll refer you to another video I made, which you find on Canvas, okay? Under videos for assignment 1, and it's called integration by parts part 3. And if you go to about the 7-minute mark on it, you'll see the technique that I would use for an exponential times a trig. You can use that same technique and apply it to this one, okay? So in order to make this video not extraordinarily long, I won't reproduce all that. So I'm referring you to that other video, but also here's how that would play out. What you'll see when you watch that other video is you have to repeat integration by parts. So I apply integration by parts once and I get this. And then I repeat integration by parts on that because that's again an exponential times a trig. So I repeat it and I get this. But then I substitute that back in there, combining steps 1 and 2, And then I noticed the original integral I'm trying to solve for is a term of this resulting equation. If I group those terms together, I get a coefficient of 2, and I solve indirectly for the integral by dividing by 2 in this case. So something like that's going to happen when you apply integration by parts to something like e to a power times sine or cosine. Okay? You'll repeat it and solve indirectly. So it doesn't really work like the other integration by parts problems that I've included in the assignment or that I've shown in other videos. Okay, so here's your antiderivative. This is what you use to evaluate the average value of that function by the fundamental theorem of calculus. So what I'll do is this. I'll take my antiderivative. Okay, by the fundamental theorem of calculus, I get this. I'm carrying over that coefficient that I factored out earlier, 6 over pi. Okay, that gets multiplied by this antiderivative evaluated between the bounds of integration. If I were to put in, oh, you know what else I did? See that 1/2 that I got when I found the antiderivative? Well, that's a constant, so I factored that out too. So I get 6 over pi times 1/2. I get 3 over pi. Then I don't have to worry about keeping track of that constant throughout the rest of my work. So, okay, from there, I put in pi into my antiderivative. It's going to look like that. I put 0 in, I get that. And I combine some terms, cancel, and I get this, 3 over pi, e to the minus pi plus 1. That's the exact answer. I noticed that my math lab said give the exact answer using pi, so that's the way I put my answer in. Maybe sometimes rounding is indicated, and if I need to do that, the average value is about 1, okay? So this thing is going to oscillate up and down, but the average value that it's going to take on this axis is about 1, all right? Okay, so that's how we can solve this one. Now, I'm aware I didn't show how to find the antiderivative. I didn't show you the work. I explained a little bit about it, but I referred you to that other video. Real quick though, I don't think the video will be complete if I don't explain a little bit about what the average value of a function is. You know, I'm saying that, yeah, this mass will oscillate up and down on the y-axis. Y will be positive sometimes, negative others, but at least as the clock runs from 0 to pi, the average value is about 1, okay? 0.996 or so. What's that mean? Okay, well, so here's our formula for the average value. Okay, here's a real simple example. I wanted one with simpler numbers. What's the average value of x squared on 1 to 3? So I use that formula and I get 13/3. Okay, so let's see. How does that come? I guess what I'm trying to say is this. We use the word average all the time. Like you might have an average quiz score. Let's say you took 4 quizzes. 95, 75, 80, 82 on 4 quizzes. Then it might be part of your final grade to find the average quiz score, which you would add those together, divide by 4, and the average quiz score is 83. Is the average value of a function anything like that? Okay? When I say for this mass on a spring oscillating up and down that the average value that it takes on the y-axis as it moves is 1, is that anything like when I average my quizzes? Or something like that? Well, here's what it actually means. So if I have my function here, okay, let's see, x squared on 1 to 3, and I'm using this simpler example for the moment, then there's a certain area under that curve from 1 to 3, okay? The average value is a curve that's constant, that has the same area underneath it from 1 to 3, okay? Now, why is that anything like averaging your quiz scores? Well, it might be that I got 4 different scores on 4 different quizzes. But if I tell you the average is 83, it would be the same if I just scored 83 on every single quiz. So I'm giving you one number that functions like if I got that score on every quiz, it would be the same end result as far as the average goes. So the average value of a function is a little like that. The function might vary across the interval you're working with. But when I calculate the average, that's one fixed number that, at least as far as the area under the curve goes, gives me the same number at the end of the day.